So a couple of quick things. Number one, as I mentioned yesterday, we will go through some generalities about the motion match lab report and the motion graphs quiz. We'll do that on Thursday. And if you need help with anything, if you're struggling because you don't know how to do graph conversions or there's things that you don't understand, then come and see me as soon as you can, and let's get that worked out. If you're mostly concerned about points, as in why did I get 7 out of 10 on the lab, or why did I get 14 out of 20 on the quiz, then wait, and we'll go over that on Thursday. I'm not going to be here tomorrow, well, I'll be here for a short time, around advisor in the fourth period. So if you have time and you want to come and see me tomorrow, you can try to track me down then. Otherwise, I'll be around the rest of the week, and you can always email me. If there's something you need, you can email me. If I don't respond, it's because it isn't a high priority. Not that I don't care about your grades, but if you email me about a grade thing, we'll deal with that on Thursday. So you just have to say bye for that. And then for the quiz, if you got less than 80% and you turned everything in on time prior to taking the quiz, you can schedule a retake. Even though you don't know what you did, we can schedule the retake, and I would like you to do that as soon as possible. You can just send me an email. I don't care when you take it. You can say, I would like to do the retake at lunch next Tuesday. I would like to do the retake on Monday during fourth period. Whenever you can do it will work for me. If I can be the proctor, I will. Otherwise, I'll just make sure that there's a quiz available and that you know where it is, and you will be able to take it pretty much whenever you want. And that will be, as I said before, up to 80%. So if you got an 80% or more, there's no point in retaking it. But if you got less than an 80%, you can schedule that retake. Since we're going to go over the quiz on Thursday, your best bet is to schedule the retake for after Thursday. And if you feel like you're really close, and once we go over it on Thursday, you're going to be fine, great. If you feel like you have a lot of work to do, then don't schedule it for Friday, or maybe even Monday. Schedule it for Tuesday or Wednesday of next week. Will you close your Chromebooks? All right, and then let's see. We're gonna, as I mentioned, we're gonna change pace a little bit here, and there's two reasons for that. The first is because this is physics, and there's three big parts of physics. One is sort of this experiential stuff. So what I would say there is, that's kind of like when you watch something move, you can see, oh, it's slowing down, it's speeding up, it's going this way, it's going that way, it's going fast, it's going slow. That's really intuitive, and most of you are already pretty good at it. Where it gets interesting is when you tie that to conceptual stuff, like the motion graphs. What does a motion graph look like? What does a position versus time graph show you? How do you use those graphs to think about how something is moving, and vice versa? That's a conceptual piece. That's largely what we've been working on up until now, but there's one more piece, which is a mathematical piece. All three of those things come together. What makes physics tricky is that all three of those are working in concert. So in a math class, for example, a lot of times you just need to know an algorithm. How do you solve a system of equations? You do this and this and this and this and this. In this class, what you'll see is while there may be algorithms, the algorithms rely, before you can do the math, they rely on you having that connection between the conceptual piece and the intuitive piece. If you don't have that yet, then the math is going to give you garbage. You'll be putting numbers in and getting numbers out, and they'll be completely meaningless. So where physics gets tricky is every time we do real physics, we're thinking about all three of those realms: the experiences, the intuitive part, the things that you're actually seeing, the conceptual part, what are these things and what do they mean and what do they tell us about the way that things work, and the mathematical part, what are the equations that we can use to make predictions and test our predictions. So part of the reason that we're doing this is because you're ready for it. We've dove into the conceptual and the experiential part. It's time to get the math started. Part of the reason that we're doing this is because I'm not going to be here tomorrow during second period, my second period. So I want to set up a class that, sorry, I was talking to the video camera. I wanted to set up something that would be easy for a sub to run, and the next experiential thing is something that most subs would not be able to help you with, because it involves technology, and it'll be easier to do it this way. So we're gonna do a bunch of math today, and then on Thursday we're gonna take the math and tie it back in with some other stuff. So that's the general stuff. Does anybody have any questions about any of those general things? Okay, so I'm gonna go through some information, and I want you to write this down. So if you haven't already gotten out something to write with and something to write on, you should do it. And this is gonna be relatively involved, so just prepare yourself. It's not over your head, but you'll have to be focused, and you'll have to write down some stuff. Like, this is stuff that you can't really avoid documenting. Yeah.
Can we open our Chromebooks so the slides, like if we need a little bit more time to write stuff down or take notes?
So in general, I prefer that you don't do that. Why don't you see how this goes? If it doesn't work for you, then we talk to me later, and then we can make a plan. Because it's hard for me when I'm looking at the back of a Chromebook, even when I know people are listening. All right. So the goal for our work today is to take the stuff that we've already been doing with motion and motion graphs and constant acceleration in particular, and tie that in with some mathematical equations. And part of what you'll be expected to do with those equations is make predictions about things. If you know X and Y and Z information, you should be able to find A and or B and or C information. There's a lot to think about here. There's a little link that I'm not going to get into today, but you'll get a chance to see in the future. If you are interested, outside of class, you can click on this and play around with it. It's kind of an interesting thing that looks at motion and with constant acceleration and making predictions and stuff. In general, here's what we've gone through so far, and I'm going to add a little bit of information as well. So we're going to start with the assumption that we're dealing with systems in which acceleration is non-zero and constant. Sometimes acceleration is zero and constant. And when that's the case, velocity won't change. And position will change at a constant rate, because you'll have a constant velocity. And if the velocity is zero, then nothing's going on at all. Those are very real conditions. Acceleration can be zero, and it can stay zero. Motion can be at a constant velocity, or things can be still. But the most interesting cases are when acceleration is non-zero, because then motion changes. And when we have constant acceleration, we end up having very predictable motion. And because of that very predictable motion, we can predict what motion graphs will look like as a result. That's not what I wanted. Hang on. This isn't working quite right. All right, hold on. I'm just going to pull all this stuff up because it's coming up in the wrong word. So when we have constant acceleration, if you were to make a graph of acceleration versus time, what you'd see is that it's a horizontal line. And the equation for a horizontal line in general is y equals a constant. The y-axis value doesn't depend on the x-axis value, when you're looking at an acceleration versus time graph, the y-axis is acceleration. So if we were to think about the variable that we use for acceleration instead of just a generic y, then the equation that we get is a equals a constant, okay? That's the equation for acceleration when acceleration is constant. Do we know what it is? Well, no, I mean, not necessarily. We just know it's not gonna change with time. It doesn't depend on the time variable at all. The slope of a velocity versus time graph is more interesting. And again, this is when acceleration is non-zero and constant. If the acceleration is zero, we get something different. But if acceleration is non-zero, then we'll get a diagonal line and the equation for a diagonal line in general is y equals mx plus b. But what's interesting about our graph is that we know that we have the velocity as our y-axis variable, and time is our x-axis variable, which means this generic y for the equation of a line is actually our velocity, v. And this x, which is our generic x-axis variable, is our time, t. And there's a couple other pieces of information that are relatively easy to figure out by looking at the graph. The first is, as we talked about yesterday, the slope of a velocity versus time graph is acceleration. That's the definition of acceleration, the rate of change of velocity. If you plot velocity versus time, then the slope of your graph will be the rate of change of velocity, which is acceleration, which means our m variable, which is the slope in the generic equation, is acceleration. And our y-intercept is a velocity. It's the starting velocity, whatever the value of the starting velocity was. That equation, when we substitute everything and rearrange it a little bit, looks like this. Our y-axis variable velocity will be equal to whatever the starting velocity was at our time period, that's the y-intercept, plus the acceleration of the object, which is constant, times time. This is an equation for a line, right? And it's an equation for a line when we're putting velocity on the y-axis, time on the x-axis, and we have a constant acceleration and some initial velocity, which might be zero. And the nice thing about this is, if we think about that special case, when acceleration is zero, then this term drops out and we just get that velocity is constant. It's the same as whatever it was when it started. So it actually works either way, even if acceleration is not zero. The shape of a position versus time graph is more complicated. This is going to be a curve. And it might be a smiley curve or part of a smiley curve. It might be a frowny curve or part of a frowny curve. Either way, it will be a parabolic curve. And for those of you who don't remember, a parabolic curve is just a curve that is generated by a quadratic equation. And so the equation, the generic equation for a parabolic curve is our y-axis value is equal to some parameter times x squared plus some other parameter times x plus some constant. And it turns out that these all match up with things that we can potentially measure. And those of you who are in calculus or getting there might recognize that this is an integral of our velocity, of our, of a line. And the line is the derivative of this equation. If you're not in calculus or pre-calculus, that's okay. You don't actually need to know that. Here's what you do need to know. This also matches up with our position versus time graph, okay? Our y-axis variable in this case is position. So our position is gonna be equal to, and then usually in physics we kind of flip these things. There's no need to, because addition is commutative, but usually what happens is we put our constant first, and then the bx term, and then the ax squared term. Our x-axis variable is time. So it's gonna be something times time squared, and it's gonna be something times time, and there's gonna be some constant here. And this is where it's, if you understand the way that parabolas are generated and you understand the calculus connections, then you might be able to figure this out. But for our purposes, you don't have to figure it out on your own. I'll just tell you that this capital A parameter is gonna be equal to 1/2 the acceleration of the object. This capital B parameter is gonna be equal to the starting velocity of the object, which usually we write as a v with a little 0. That's velocity at time 0. And the constant is whatever the initial position was, the y-intercept. So this equation and this equation are equivalent when we have position plotted versus time under the conditions of constant acceleration. This is a parabolic curve, this will be a parabolic curve as well. These two equations are equivalent, and these two equations are equivalent. So there's a connection between what we see when we have an object that's moving with constant acceleration. That's the part that you all understand intuitively. When I roll this cart up, every single one of you could predict what's gonna happen. You know it's gonna slow down until it gets to a high point, and then it's gonna speed back up as it comes down the ramp. If I were to start the cart up here and give it a little push down the ramp, you know it's just gonna speed up and go faster and faster. This is easily predictable motion intuitively. As you learned, I hope, yesterday and last week, that makes graphs that are also predictable. Velocity graphs that are diagonal lines, acceleration graphs that are horizontal lines, position graphs that are curves. And here's the math behind it. Here's your position graph, which is a curve, your velocity graph, which is a diagonal line, and your acceleration, which is a constant. If we take our acceleration and say that it's 0, then this term drops out, and we get a horizontal line for velocity. This term drops out, we get a diagonal line for position. If we say that our initial velocity is 0 as well, then this term drops out and we get v equals 0. If v equals 0, then this term is 0. If a equals 0, then this term is 0. And we get x equals a constant. We get an object that doesn't move. The equations work even when acceleration is 0 and or initial velocity are 0. All right? So this is what we're going to be operating with today. These two equations, we're going to take these along with some, like, a little bit of definitional magic, and we're going to turn it into a way of making predictions with not that much information, as long as we know that acceleration is constant. Before we launch into that, I want to go through some variables, because you're seeing already things are coming into play that we haven't necessarily talked about yet. We've been using time as a variable, but we haven't put it into an equation. And all these like zeros and things like that, it's getting a little messy. So let's nail some things down. Let's talk about variables and let's talk about units. This is stuff, this won't take you long to write. You will need to be using these terms so that we're all communicating on the same level. You'll find the book might use some different terms. And online, they might use some different terms as well. The ones that I'm going to use are the ones that are most commonly used in physics and are used on the AP Physics exam. which is not a big deal for you, but it's gonna keep our language in common with what most other students in the US are looking at. Okay, so when we look at our variables so far, we've talked about position, we've talked about time, we've talked about velocity, and we've talked about acceleration. So let's make sure we know what those variables are going to be and what the units are going to be. For time, we always are going to be thinking in terms of a time period. Things move over time. So if we want to make predictions about things, what we want to know is what's happening at some earlier time and what will be happening at some later time. Or maybe if we know that this is happening at some later time, then can we make a guess about what was happening at some earlier time? In general, the earlier time that we talk about is going to be the letter T with a little 0 on it. That stands for initial time, or time at time 0. Time is relative. Like, when is time 0? The beginning of the universe, the start of the earth, the start of the formation of Earth? Is it midnight of every day? Is it when you start an actual physical stopwatch? The answer is time 0 is whenever you say it is. And at some later time, we'll say that it's time T. Which means that our time period, the time period that we're considering, is always going to be the difference between those things. So delta T is going to be equal to T minus T0. The delta, as we've talked about before, stands for change. The change in time that we're considering for various scenarios is just the difference between the current time and whatever we decided the initial time was. A lot of times this time 0 is actually going to be 0 seconds, right? And that means that our final time minus 0 seconds is going to be equal to our change in time. So what you'll see frequently, and you'll see me using this as well, people will use this as a shorthand for delta T. And 75% of the time that works great. The other 25% of the time you will mess something up because your initial time wasn't 0. And then you can't just use the final time, you actually have to do the subtraction. For all three of these, our units in general are going to be seconds. That's not the only unit we can use. I don't want you to get concerned about unit conversions. There may be problems that you come across that I don't write that involve unit conversions. And in general, the trick is just make everything seconds. Make everything seconds as soon as you can. If you're given times in hours, that's 3,600 seconds. If you're given times in minutes, that's 60 seconds. Days, years, whatever, just change it all to seconds. It's a pain in the butt, but do it. I'm not going to give you times except in seconds, because doing those conversions, I think, is just an exercise. It's just a way to get you to make a mistake, basically. And I don't want you to make mistakes. I want you to be able to understand physics. All right, when we think about our initial position, just like time, that's an arbitrary thing. What was my initial position? Well, when I woke up this morning, I was in my bed. When I started driving to work this morning, I was in my driveway. When I started class today, I was standing right there. And right now, if I want to say what happens next, my position is right here. Initial position is arbitrary. We get to decide what time period we're looking at. Either way, we just refer to that as X with a little 0, initial position. Once we start dealing with vertical motion and or motion in 2 or 3 dimensions, this could also be Y or Z. There's no magic to it. If I say an object's position Y is something, that's just going to be a number with a positive or negative associated with it. And unless you're told more about the problem, you shouldn't necessarily assume any orientation. And final position or current position, we use the same convention, we just call that X. So it's a weird thing because X refers to generic position. It also equals like a current or a final position. This is all shorthand stuff. So if we were to look at this in terms of functional notation, you'd see there's a lot more to it, but nobody likes writing. So we all in physics do shorthand as much as possible. And that means that displacement, which is change, hang on, there's not a spot for that. Displacement, which is change in position, is gonna be final minus initial position. We've looked at this already. So you know this equation already, but just to make sure that you see it, there it is. And that will always be measured in meters, so we'll keep it simple and just look at things in meters. And then our initial velocity, at this point I think you're probably expecting what I'm gonna write. Our initial velocity is v0, and our current or final velocity is v. Where things get a little bit interesting is when we start having more than one dimension. So as we start adding dimensions, we're gonna have to add a letter to indicate which dimension we're talking about with the velocity. So you might see, for example, v0x, or v0y, or even v0z. And same with v. You can have vx, vy, v whatever else. You don't have to worry about that for now. Just know that, we'll need to use that down the road. Those units will always be meters per second. And if you need to find change in velocity, which you will, it doesn't have a special name, it's just called change in velocity, then just like displacement, you just subtract. So it's final minus initial. And then lastly, we have acceleration, and acceleration's a little bit easier just because we're not gonna change it. So there's not gonna be an initial and a final or a change in acceleration. We just use the letter A. We might need to think about different dimensions. So we might have an AX and an AY, and or an AZ if we're using 3 dimensions. And the units for acceleration are a little weird. For those of you who are interested, I can show you later where this comes from. But the units are meters per second squared. It tells you how many meters per second something's velocity will change per second. Meters per second, which mathematically reduces to meters per second squared. So we're gonna add lots of variables over the course of the year, but these are the ones we're gonna start with. With these variables and the equations I showed you earlier, and one more kind of cool, definitional equation, we can build 4 really useful equations that end up allowing us to make lots and lots and lots of predictions about where things will be, how fast they'll be going, what their acceleration will be, as long as acceleration is constant. Those 4 equations are sometimes called the big 4. Mr. Kirsch calls them that, and some other people do too. Or you might just hear them referred to as the kinematic equations. And the thing about the kinematic equations is they all hinge on acceleration being constant. So for all of the equations, we have to make sure before we use them that we're actually dealing with a situation in which acceleration is constant. If acceleration is constant, these equations will work mathematically, but they won't give you meaningful answers. The answers you get will not be related to any real motion in the real world, okay? So here are those 4 equations. First, the equation that relates an object's final position to its initial position, initial velocity, and acceleration. This is the one that looks like a parabolic curve, and it just looks like this. And because we're referencing the x variable for our position, that means for this specific equation, we're actually looking at the initial position in that x direction and the acceleration in that x direction. For the problems we're going to start with, you don't really need to worry about that because the problems we're going to start with are all one-dimensional. Once we start looking at 2 dimensionals, then we're gonna have a y here sometimes, and this will be a y, and this will be a y sometimes. And you have to keep everything separate, because each dimension will have its own initial values and its own acceleration, okay? The next equation is the linear equation that you get when you're looking at predicting an object's velocity, when you know its initial velocity and its acceleration. So our final velocity will be equal to the initial velocity plus the acceleration times time. And again, this is a one-dimensional equation. So for any dimension, the velocity in that dimension, like the x dimension, will be equal to the initial velocity in that dimension plus the acceleration of that dimension times the amount of time that goes by. Time isn't a spatial dimension, so we don't have to worry about an x or a y or a z for time. The same amount of time goes by as an object moves three-dimensionally in each of those dimensions. All right, and then, yeah.
Wait, so what does the OX mean?
O means initial. X is telling us that we're dealing with whatever axis we've defined as the x-axis, the x dimension. For now, you don't have to worry about the x part of it, because everything we do is going to be one-dimensional. But we do have changing velocities over time. This, with the 0, is the earlier one. Without the 0 is the later one. And then there's a couple of equations that come from a kind of a neat mathematical piece. So as a quick aside, here's that neat mathematical piece. If you look at an object's velocity over time with constant acceleration, what you'll see is that if its initial velocity is v0 and its final velocity is v, because it's a line, the average velocity will be equal to the mathematical average of these two velocities. It'll be equal to the initial velocity plus the final velocity divided by, divided by 2. Just the mathematical average of those things. And that's because it's a line. So, I mean, the mathematical average of the y values of that line will tell you the middle value, which is the average. But we have a definition for average velocity as well, and it's related to displacement. So we also know that average velocity is defined as an object's displacement. Why can't I write what I'm thinking? Why can't I write what I want? All right. So it's an object's displacement divided by the amount of time that goes by. And that is final minus initial position divided by the amount of time. So what that means is we have an additional equation that we can use that relates all of, a bunch of these variables, which is this average velocity and this average velocity are mathematically equivalent. So displacement divided by the amount of time that goes by will be equal to the mathematical mean of initial and final velocity. This is not one that you're going to use very often. Sometimes you'll need it, but not very often. But if we take this equation and we combine it with these two equations, then what we get is something that's really useful. And it's this equation right here. An object's final velocity, and we'll just look at the x dimension here, will be equal to, its final velocity squared will be equal to its initial velocity squared plus 2 times its acceleration times its displacement. That's a weird equation. It's not something where it's like, well, this comes from some graph. This equation comes from these two equations and this definitional relationship. Under conditions of constant acceleration, average velocity is the mathematical mean of initial and final velocity. And average velocity is always defined as displacement over time. If we take this equation and do some creative substituting into these two equations, this one pops out. And here's what's cool about this one. It doesn't have time in it, which means we can make predictions about how fast things are going to be going or where they're going to be, as long as the acceleration is constant, if we know enough, even if we don't know how much time is going to go by. And that seems kind of crazy. Like, if I tell you, like, car is going, 20 meters per second, and it drives for 15 meters at a constant acceleration of 2 meters per second squared, how fast will it be going? Our instincts are, well, we need to know how long it's been driving. We can't make a prediction unless we know how much time goes by. But it turns out, under conditions of constant acceleration, we don't actually need to know that. We just need to know enough of these things to be able to put together the rest. It's really kind of neat. Yeah?
But like in the question, like how fast is it going? Just like when?
Well, how fast is this going is this. It's the final velocity. You could find when as well. You can find time from that information as well. But you don't need to know the time in order to know how fast it's going to be going, provided you know how far it goes, what its initial velocity was, and what its acceleration is.
So like it's just like skipping the step of finding.
It's skipping the step of finding time, yeah.
If you know that like you can just divide something by 2, which is just the equation, but just like, do you have to write out the whole thing and then plug in zeros and like show that like there's nothing there, or can you just write, like, or do you accept an answer that's just?
I'll show you how to do it, and what you'll see is that there's a system. There is some stuff that you have to document, but you don't necessarily always have to like show me where the zeros are and stuff like that. Okay, so these equations we're going to be able to use to make all sorts of predictions. I'm going to throw out a couple of things that are sometimes a little bit less than obvious, one of which I want you to write down, and then there's some stuff that you're not going to need to write down. And then I'm going to show you a system for solving equations, and we'll practice a problem, and then you'll have a bunch of time to do some work. One condition that I mentioned yesterday in which we have constant acceleration is when things are in the air and not supported by anything else. So when you throw something, it's just in the air. Now, some of you might be like, well, what about air resistance? And that is true. We in general are going to ignore that. We're going to deal with objects that are moving on a time scale such that we don't have to worry about air resistance too much. So in general, when we have objects that are in the air that aren't being held up by anything, we're going to have a constant acceleration of about 10 meters per second squared toward the ground, straight down. And we can say that this is any axis in any direction that we want. But it's going to be very common that we use a frame of reference where down is negative and up is positive, and we will often call this the y dimension. And in that case, if we use that reference frame, then our y acceleration will be negative 10 meters per second squared. That's only if we're using this reference frame, which is what we're going to use most of the time. If we know something is moving in free fall, then instead of using that x variable, we usually just use y instead. Because that way when people look at it, they're like, oh, it's vertical motion. It's not a requirement, but typically that's what happens. So if we were to make a graph of velocity versus time, what we'd be looking at is a velocity graph that shows the final velocity in that vertical dimension, the y dimension, over time. And no matter what the initial velocity is, it's gonna become more and more negative over time. So what we would expect to see is a diagonal line going down and to the right. It might start off going up, slow down, reverse direction, and come back down. Or, a lot of times, we just drop things, which means the initial velocity might be 0. Or we could throw things down, push them down, so their initial velocity is negative, and then it just keeps going faster and faster. And this is what the velocity will look like the entire time it's in the air. As soon as it touches something else, the ground or whatever else it lands on, then we're no longer dealing with free fall, with acceleration. The acceleration will change, and we're not dealing with constant acceleration. So when we deal with things in the air, generally what we're thinking about is their motion from the moment they're unsupported by anything till the moment right before they hit the ground or hit something else. And that's a weird thing to think about, because usually what we're like is like, well, if you throw a ball, eventually it stops, so its final velocity is 0. But in free fall, we think about the final velocity as being how fast something is going right before it hits the ground. Yeah. Okay. All right. So I told you there's an algorithm for dealing with these problems. I'm gonna walk you through the algorithm, and then I'm gonna give you a bunch of tips that you don't have to write down. And then I'm gonna solve a couple sample problems, and then you're gonna be on your own. So here's the algorithm. And I'm gonna underline the parts that you should write down. You don't have to write all of this down. You can always come back to this and look at the presentation. But basically what you need to start with is draw a picture. And on that picture, you should identify 0, 0, the location of your origin. If it's one-dimensional, then you only have 1 0. So for now, we're only going to be dealing with 1 0. And which direction is positive? You only need to identify one direction, because the other direction will be, the negative direction will be opposite of that. Okay. So your first step, draw a picture, tell me where 0, 0 is, and show me which directions are positive. The next thing you're going to do is break vectors into components. Write that down and then forget about it, because we're going to talk about that when we get to two-dimensional motion. It's its own big thing. Some of you already understand vectors and components and can do the mathematics. Some of you can't yet. We're not going to talk about that right away. So it's got to be in there, because that eventually is going to be an important part of the algorithm, but for now, it's not. The next thing you're going to do is identify the values of the variables that you know, and identify which variables you don't know. And then you're going to pick a kinematic equation, and you're going to solve it. To start with, it's going to be relatively simple. There's going to be an obvious equation that has the stuff you know and contains the variable for something that you don't know. And that's going to be what you're trying to find out. Down the road, things are going to get more complicated, because what you'll have is maybe several things that you don't know. And there might be several steps to the problems where you solve one part of a problem to get one piece of information. Then you use that information in another part of a problem to get a third piece of information, or a second piece of information that you then use to get whatever the answer is that you're actually looking for. But to start with, we're just going to keep it simple. We'll just be finding one thing at a time. When there are multi-step problems, like the one I'm about to go through, you'll be led through the process of finding each part. Down the road, that won't be the case. Down the road, you're gonna have to figure out some of this stuff on your own, but we'll start sanely, okay? And then something to consider, and you don't need to write this down now, but something to consider is problems that don't come from me may not be in our units of meters, seconds, meters per second, and meters per second squared. So if you're given a problem and it's got feet, and years, then you have to do some unit conversions. I'm not gonna ask you to do that, but somebody else might. And then, you may have problems where the acceleration isn't the same during the whole scenario. I'm gonna solve an example problem for you right now that looks like that. And so in that case, what you really have is two problems, or maybe three. Each little section of constant acceleration is its own problem. Those can get ridiculously complicated. Sometimes they're ridiculously complicated for stupid reasons, like whoever wrote the problem just wants to trick you. Sometimes they're complicated because reality can be complicated, okay? All right, here are some things that you don't need to write all this stuff down. I'm gonna just like show you some stuff, or highlight a couple things to write down, but you can always come back to this slide and look at it later, and eventually what's gonna happen is you'll internalize all of this stuff, okay? So these are tricks, and this is where the question that you asked when you came in, you may have already figured part of this out. But here's the deal. Number one, when you have an object that is moving in the air in free fall, if it goes up and then down, at the highest point of its motion, its velocity is 0. And you don't have to write this down, just like no, there's little tricks, and then as you're doing problems, what'll happen is you'll have a problem, you'll be like, wait, there's not enough information. As soon as your brain says there's not enough information, come to this slide, because the information is there. Here's how we know that its velocity has to be 0. Because if we have something that is moving in the positive direction, and then it's moving in the negative direction with constant acceleration, its velocity versus time graph is going to be a diagonal line. It crosses the x-axis. At that moment, its velocity is 0. It doesn't stay 0 for any length of time at all. It's an infinitely small amount of time that it's not moving. But at that moment in time, its velocity is 0, and that's a known thing, which means you can put that into your equations. Yeah?
Will the problems we're doing, will it be like kind of piecewise, because it will be
To
like
start with.
speed up?
To start with. And then eventually, they will combine things. Yeah. Another trick is, oh, that's funny. That's out of order. But another trick, as I told you before, is that in free fall acceleration, it's always down at 10 meters per second squared. If you say that down is negative in your y dimension, like most of the time we will, then that means that any time something is dropped or thrown or kicked, it will have